Hey guys, how you doing? This is Coach Scott with Purple Wave Chemistry. Let's go further into Unit 6, talking about intermolecular forces. Now we're going to talk about properties that IMS affect. Let's talk about surface tension, viscosity, and vapor pressure. All right, so most of us know what surface tension is, or we think we do. So let's think about what causes it. So these IMFs will attract many properties, will affect many properties. So the strength of these attractions that are between the molecules will affect what's going on with these things. Let's talk about viscosity, right? We've got two types of viscosity shown here. This is notice a very low viscosity, it's like water. This is a very thick viscosity, right? It's slow. It's like a molasses or something along that line. So what is viscosity? It's the resistance of a liquid to flow. Or I'm going to say this a little different. It's the resistance of a fluid to flow. We call that viscosity. It's related to the ease with which these molecules can move past each other, right? As they can move back and forth from each other, that's what the viscosity is. So viscosity will increase with a stronger IMF. And it's also going to decrease with a higher temperature. So which one's more viscous? Well, of course, that pink purple one would be more viscous because it's resisting the flow. So let's look at some of these bigger molecules. You got hexane, heptane, octane, nonane, and decane. And those are on the number of carbons there, right? You can see as the number of carbons go up, all right, you get bigger, there's more resistance to flow, right? So your viscosity increases. So surface tension, okay, will result from a net inward force and is experienced by these molecules on the surface of a liquid. It almost, because these molecules right here are holding on to each other, it almost makes a skin on the surface of a liquid. You got these little water spiders right there walking around on the surface of water due to the surface tension. This is directly related to the attractive forces between the molecules. The stronger the attractive force, the more surface tension is needed to increase the surface area of that liquid. So water has a very high surface, pretty high surface tension of 7.29 times 10 to the minus 2 joules per square meters at 20 degrees C. This is all related to temperature, right? But mercury has a higher surface tension of 4.6 times 10 to the minus 1 joules per square meters. Why do you think mercury has such a high surface tension related to water? Let's look. Mercury has metallic bonds, and these metallic bonds are much stronger than hydrogen bonds. So, the next one is vaporization or vapor pressure. So, boiling and evaporation, there are two ways in which liquid will vaporize into a gas. Now, there's some distinction between these two processes. One, boiling occurs at a specific temperature. We call it the boiling point. It will occur throughout the entire liquid, and it is achieved when atmospheric pressure equals the vapor pressure of the liquid. Evaporation will occur below the boiling point, and it will only occur at the surface of the liquid. Vapor pressure is measured as the pressure exerted by the gas on top of that liquid above the surface. All right. So if you look at sample A, it has a lower temperature, shows some vapor pressure above the surface of the liquid. All right. Sample temperature or sample B, you've got a higher temperature, but you've got a greater number of vapor particles. You're going to have a higher vapor pressure. Volatility. This is another characteristic of a liquid that's based upon the strength of its intermolecular force. The more volatile a liquid, the more quickly it evaporates. the higher is vapor pressure at a given temperature, and the weaker its intermolecular forces. We use acetone to dry glassware in chemistry lab. I do. Right? Why? Because it's very volatile. Right? It will quickly evaporate. It's got a much higher vapor pressure. And looking right here, let's see. This is a vapor pressure curve. At any temperature, some molecule in a liquid has enough energy to escape. All right. So this is the kinetic energy of that molecule. As the temperature rises, the fraction of molecules that have enough energy to escape will increase. All right. So this is a measure of temperature. I think this is the Boltzmann diagram. So this is the fraction of molecules with the kinetic energy enough to escape. So at temperature at 300 K, there's a whole bunch of stuff being escaped. Now this is just the numbers. This is the E sub 0, E naught. Okay, and this is the molecules that have enough kinetic energy to escape. Right? They're moving quicker. So vapor equilibrium, the liquid vapor, as more molecules escape the liquid, the pressure is going to increase because it just increases. So as the amount of pressure increases, the amount of force per unit area also increases. So when the liquid and the vapor reach this dynamic equilibrium, the number of molecules evaporating and the vapor molecules condensing are at the same rate. You're at equilibrium. So we have what we call vapor pressure curves, and these are sort of important. All right. So this curve is made up of an infinite number of points. Each point along that curve shows the temperature at which the atmospheric pressure equals vapor pressure. So anything above that, well, what's going to happen? There's our boiling point, our normal boiling point at normal pressure, 760. You can see that water has a much higher boiling point. Why? Because its vapor pressure is much higher. So here the vapor pressure is much lower with the diethyl ether. Ethanol 78.3. Ooh. So the boiling point of that liquid is when the temperature of the vapor pressure equals atmospheric pressure. So the normal boiling point of the temperature, which is vapor pressure, is 760. Because that's our normal pressure, standard pressure. 1 atmosphere, 760 milliliters. So this diethyl ether at a lower pressure, let's say around, I don't know, that's about 450 atmospheres or millimeters of mercury. All right, the boiling point would be 20. Water, as we lower the pressure, as we get pressure down to like, I don't know, that's about 50 millimeters, your boiling point would be 40 degrees C, our room temperature, right? So that's how we can determine this. And this goes into play of one of my wife's favorite tools, the Instapot, which is all it is a pressure cooker. She loves the Instapot. So this liquid is going to boil when the vapor pressure equals atmospheric pressure. So if we increase the atmospheric pressure with a pressure cooker, so the water's not going to boil away at 100, it can be heated up to like 120 before it starts to boil or turn to steam. So we're raising the cooking temperature, and this causes the cooking time to decrease drastically, which is why the Instapot's so cool. Here's just a picture of what we're doing here, right? So you can put some brown rice in your Instapot, all right, instead of cooking for 50 minutes, you know, that stuff done in about 20 minutes. It's pretty cool. This is an old-fashioned Instapot. It's called a pressure cooker. All right, now let's look at boiling point and pressure. So boiling will occur when the vapor pressure equals the atmospheric pressure. Now, if you were to go on top of Mount Everest, your atmospheric pressure becomes much lower. All right. So that that means what? That the water will boil much, much lower than when we're at Memphis, which we're almost at sea level. Right. We'll watch a little video about that. So anyway, guys, that's talked about viscosity. We talked about vapor pressure and some other things that the intermolecular forces affect. And we'll come back and we'll talk some more about some things with IMFs. So this is Coach Scott saying, hullabaloo, connect, and have a great day.